Hello, this is Professor Matt Katroulis of Rio Hondo College. This video will focus on Chapter 10, which introduces the subject of organic chemistry. Now, before we get into organic chemistry, I'd like to note that beginning with this chapter, we head in a new direction relative to what we had covered so far. Chapters 1 through 9 were largely focused on, for one, more mathematical topics, such as the mole, measuring molarity, solution concentrations, and things like that. In this chapter, we move off in a different kind of direction and focus on the chemicals which play a more direct impact on life. So let's define organic chemistry. First, let's start with just a bit of history. Up until very recently, it was thought that many chemicals came only from living beings, and those were called organic chemicals, while all the remaining chemicals, things that you would find in minerals and rocks, were considered to be inorganic chemicals. And it was thought that there was a big separation between the two, and from one you couldn't get the other. The scientist Wohler was able to show that this was not the case. He was able to produce an organic compound, urea, which is found in urine, by only using inorganic chemicals. So, in effect, it is not true that there is a difference between chemicals produced by organic beings and non-organic sources. So, we've redefined organic chemistry as the chemistry of one very important element, and that is carbon, and the various compounds that it produces. Now, to make life easy, we're going to say that essentially every compound that contains carbon is organic. In reality, that's not usually how we classify chemicals. For example, pure carbon, like in the form of diamond or charcoal, is generally not considered organic, nor is carbon dioxide. However, I think that confuses things a bit, so as I said, we're just going to keep to a very simple definition that if a chemical compound contains carbon, we will call it organic. Inorganic compounds are pretty much all the other compounds that are left out of this definition. So water, for example, would be considered inorganic because it does not contain carbon. Now, carbon is extremely important for life, and with the exception of water, most of the really important chemical compounds in our bodies contain the element carbon. And these are found in chemicals whose names I'm sure you've heard of before, such as carbohydrates and fats and proteins, as well as DNA and RNA and other important chemicals. We also encounter carbon a lot in our daily lives. For example, compounds of carbon make up gasoline. Plastics are largely composed of organic chemicals. So it's really hard to avoid organic chemistry just getting through average daily life. Now, organic chemicals don't contain only carbon. Essentially, all of the organic chemicals which we're going to see contain hydrogen as well. Many of them contain oxygen or nitrogen. Some of them contain the halogens, especially chlorine, bromine, and iodine. Fluorine isn't quite as important when we're dealing with organic chemicals. Sulfur also has a minor role, and phosphorus less so. Now, when we talk about bonding in organic chemicals, the bonding is essentially exclusively covalent. Well, why would that be so? Well, let's take a look at the elements that we're considering. Carbon, hydrogen, nitrogen, oxygen, etc. All of those elements are nonmetals, and we already saw that the primary form of bonding amongst nonmetals is covalent bonding. So it only makes sense that we're going to focus on covalent bonding in this chapter and the coming chapters. Now, hydrogen, as we've already seen, makes only one bond in any of its compounds, and we will never encounter lone pairs on hydrogen atoms. It's vitally important to understand that carbon will always make 4 bonds in all of the chemicals that we're going to be talking about from here on out. So that's a very important bonding pattern, probably the most essential for understanding the material that's coming up. So as we can see here, hydrogen will make 1 bond, and I haven't shown what it's bonded to over here. So this line is just representing a bond to some other atom. There are 4 ways in which carbon can make 4 bonds. It can make 4 single bonds. Carbon could make 2 single bonds and a double bond. It can make a single bond and a triple bond. And much less common is carbon making 2 double bonds. Outside of carbon dioxide, we're not going to really see that bonding pattern. So these 3 are going to be of particular note for the material that we're going to be coming up to. The word heteroatom is used to define any element which is not carbon or hydrogen. So we've already gone through a list of other important elements. Oxygen and nitrogen are the most important of the heteroatoms that we will see. And then we already mentioned the halogens and sulfur as other heteroatoms. It helps us a lot if we know the bonding patterns for all these elements as well. Nitrogen will usually make 3 bonds and has 1 lone pair. Oxygen will have 2 bonds and possesses 2 lone pairs. And then the halogens make 1 bond and have 3 lone pairs. As we go down the periodic table, we find that elements tend to mimic patterns of the elements above them. So for example, sulfur is right below oxygen. So it's very often going to follow the same bonding pattern as oxygen does, meaning that it will have 2 bonds and 2 lone pairs. And so here is a summary of the most important bonding patterns that we see for chemicals in organic chemistry. And it's very important that you put this to memory. So hydrogen, 1 bond. And now if we think about this in terms of the periodic table, carbon is in group 4. So it starts off with 4 bonds. As we move to the right on the periodic table, we go down by 1 bond and then add a lone pair. So moving to the right, from carbon to nitrogen on the periodic table, we now have 3 bonds, 1 lone pair. Moving to the right again on the periodic table, to the right of nitrogen is oxygen. So oxygen has 2 bonds, 2 lone pairs. And then the halogens, so fluorine and all the elements below it, 1 bond and 3 lone pairs. You'll notice that these numbers in the rows all add up to 4. 4, so 3 plus 1 is 4, 2 plus 2 is 4. Why is that? Well, if you'll remember, all of these elements must follow the octet rule. Every bond contains 2 electrons, so 4 times 2 would be 8. Carbon with 4 bonds is meeting the octet rule. Nitrogen here with 3 bonds, that would be 3 times 2, or 6 electrons in the bonds. And a lone pair has 2 electrons, so 6 plus 2 would be 8 electrons. Nitrogen is satisfying the octet rule. So this is all in accordance with all the material that has gone before it. The first major grouping of chemicals that we're going to deal with, and this will be the focus of chapter 10 and 11 in particular, are what are called hydrocarbons. And the word itself should pretty much tell you what it means. It's compounds which contain only hydrogen and carbon. We are going to classify them into 2 groups here. First of all, the unsaturated hydrocarbons. Unsaturated hydrocarbons have at least 1 double bond or a triple bond. And those are going to be the focus of the next chapter, chapter 11. And then saturated hydrocarbons, which are ones that contain only single bonds. And that will be, after some introductory material, the focus of this chapter. Technically, the word saturated should not contain compounds that contain rings, but for reasons of simplicity and understanding reactions, we're not going to consider those as being unsaturated. We will consider all of the chemicals that we deal with in this chapter to be saturated. The first really important subject to get out of this chapter is understanding how we represent organic chemicals with drawings. So expanded formulas are most similar to what we've done before with Lewis structures. So an expanded structure shows all atoms and all bonds. So for example, this chemical here, which we're going to learn is called propane, is showing a carbon making its 4 bonds, and this carbon making its 4 bonds, and this carbon making its 4 bonds. And we'll see that all of these hydrogen atoms are making 1 bond. They're all following the common bonding patterns as mentioned before. You'll notice this compound here, which is called methyl cyclopentane, is also following all of the bonding patterns. But there's a lot more hydrogens here than there is in propane, and that somewhat clutters up the picture. So we're going to want a simpler method of representing organic chemicals, because all of that detail really obscures what we need to see. And so we have a few other ways that are useful to us. So one method is what we call skeletal structures. And in skeletal structures, we actually focus almost on the bonds instead of the atoms, so to speak. And so we use lines to represent each covalent bond. 1 line represents a single bond. 2 lines parallel to each other represent a double bond. 3 lines represent a triple bond. And the lines are going to show us the connection of carbon atoms. So wherever any 2 lines intersect is understood to be a carbon atom, and the end of any line is also understood to be a carbon atom. So let's take a look at how skeletal structures work. We'll start off with a simple example, and that is propane, which we already saw as an expanded formula. We saw that propane has 3 carbon atoms, and that's going to be our focus right now, just the carbons. So we show that by putting our pencils down on a page of paper, and that first point stands for a carbon atom, and then we draw that up to another point and stop, and that's another carbon atom, and then we draw it down to another point, and that's the next carbon atom. We have to draw these as a zigzag, because if we just drew a single long straight line, it would be thought to be just a carbon at one end and a carbon at the other. So we zigzag as we go. And then down here, we are showing, again, methyl cyclopentane. So we have 5 carbon atoms in a ring. So I represent that ring as just a simple pentagon. And then we draw that up to the next carbon, which is represented by that point right there. So you see, what we're really showing here is we're highlighting the bonds between carbon atoms. Now, to understand this a little bit better, let's go into a little more detail. You saw that the structures didn't show any atomic labels, and it didn't really show any information about those hydrogen atoms. It's understood that since carbon must make 4 bonds, any missing bonds, if we're looking at the number of lines coming out of a point, and they're not adding up to 4, well, anything missing indicates that there must be a hydrogen atom there. Now, we do draw labels for all the other atoms, including nitrogen, oxygen, phosphorus, etc. And we also are allowed to draw in carbon and hydrogen. They just are not required when we're drawing a skeletal structure. You always do need to show hydrogens which are bonded to heteroatoms. So, for example, oxygen bonded to hydrogen, that hydrogen has to be shown. Any hydrogens bonded to nitrogen, those must be shown as well. So let's go back and look at that picture again to get a better idea as to how this works. So since this point here represents where 2 lines are intersecting or are meeting, that indicates a carbon atom. There are 2 lines coming out of it, so that counts as 2 bonds. Carbon has to make 4 bonds, So since we only see 2 bonds coming out of there, that means there must be 2 hydrogen atoms there to get to a total of 4. And that carbon atom right there is represented by this carbon in the middle. What about these points here? Well, this point represents a carbon atom, and it has 1 bond coming out of it. So since carbon must make 4 bonds, if we only see 1 line, that must mean that there are 3 hydrogens, which we do not see. So this is a carbon with 3 hydrogens. The same thing for that point over there. That's these 2 carbon atoms, and there are 3 hydrogens here. The same is true down here. This point is a single carbon atom, and since there's only 1 bond coming out of it, there must be 3 hydrogens there to get to our total of 4 bonds. So that corresponds to this carbon right here. How about this carbon right here? This is where, again, some lines are meeting. So this carbon is showing 3 bonds to carbon atoms. So there must be 1 hydrogen atom there. And that would be this hydrogen right here, so we're leaving it out. And then all of these points right here are carbon atoms with 2 hydrogen atoms on them. This might seem a little bit tricky and confusing at first, but I promise you with a lot of practice you won't have difficulty seeing the hydrogens there. Now, one other point to make really quickly here. Here we see a carbon atom with 3 lines coming out of it. That's totally fine. We might see carbon atoms with 4 lines coming out of them. That would be fine. But you could never expect to see a carbon atom with 5 or more lines, because then that carbon would be exceeding the octet rule. It would be making 5 or more bonds, and that is definitely not allowed. Now, we're going to limit our use of skeletal structures somewhat in this class. Line drawings is another term for skeletal structures, and that's what I have written right there. So what I'm going to do is I'm going to use line drawings to only represent rings most of the time. And all of the other carbon atoms which are attached to those rings or not involved in rings, I will generally show as written out. So this carbon is understood to have 3 hydrogens on it right there. That's a way of showing it. That's a little bit easier to understand, I find, for most people than drawing it this way, which is perfectly acceptable. I see that point as a carbon with 3 hydrogens on it, but I think this makes it easier for most students when they're first dealing with structures. Condensed structures are another way of showing organic molecules, and they're kind of a happy medium in between expanded formulas as well as the line drawings that we just saw. So we do show the hydrogens and we do show the atom labels, but what we do is we show all the hydrogens attached specifically to the carbons that they're in, and we number them. So for example, CH3 would indicate a carbon with 3 hydrogens on them. And we can sometimes show lines between the different labels, but we are also allowed to leave those out if we can do so without it being ambiguous. So let's take a look at how this works. So again, going back to propane here, our carbon with 3 hydrogens, carbon with 2 hydrogens, carbon with 3 hydrogens. We can abbreviate that by just saying, well, this carbon has 3 hydrogens. Let's not show all those bonds. So we just write CH3. And then I'm drawing here a bond, which is that bond from this carbon to this one. This carbon has 2 hydrogens, so I just write CH2. And then I draw the next bond to the next carbon with its 3 hydrogens. Now you have to be very careful when looking at these formulas. You must understand that this carbon is not bonded to hydrogen. Any hydrogens that are drawn after a carbon are understood to be bonded to that carbon. So these 3 hydrogens belong to this carbon. This bond is between the carbons. These 2 hydrogens belong to this carbon. This bond, again, is between the carbons, and then these 3 hydrogens belong to this carbon. Now, we don't really need either of these bonds to be shown. It would be simple enough if we just wrote out CH3, CH2, CH3, And we can kind of see here that this carbon has to be joined to this carbon because they're listed sequentially. And then this carbon must be bonded to this carbon over here. Okay, so either of these would be considered acceptable condensed structures. Let's take a look at another compound here. So we have 4 carbons in a row here, and then a carbon with 3 hydrogens, as it were, dangling off of this chain of carbons. So we can abbreviate it by just saying this is a CH3, so CH3 right there. This is a carbon with 1 hydrogen, bonded to a CH2, bonded to a CH3, and then this carbon has, again, what we call a branch to this CH3 here. Now, it's fairly simple to remove these 3 bonds here. That's not too much of a problem. But I think it's kind of risky to remove this bond right here, because it would be kind of ambiguous if we were to try to do this in another way. There is another way we could represent this formula, and that is, instead of drawing this CH3 down here, we could put the CH3 in parentheses and a 2 after it, but I find that to be very unclear, so I'm going to stick to using methods like this exclusively. So let's practice. So I'm going to now draw for you several different compounds, and I'm going to draw them in different representations. Some of them in expanded formats, some of them in skeletal formats, some of them in condensed structures, and we want to practice translating these molecules from one form to another. And it's very important that you get used to writing these structures out by hand. It's not good enough just to watch me do it. So I'm going to do all of this next part by hand. I want you to copy down what I draw and then practice making the new drawings. Here's the first molecule, which I would like you to draw. You'll notice it contains a carbon ring containing 4 carbon atoms. Branching off of the ring is a group containing 2 carbon atoms with their hydrogens. And on one of the carbons there's also a chlorine atom, which has 3 lone pairs. Unfortunately, the top lone pair is cut off. And I would like you to represent this as a skeletal structure. Again, those are called line drawings. And then as a condensed structure as well. Please go ahead and pause the video and return once you're done. Assuming you've paused, we're going to continue drawing these. So we'll represent the 4-membered carbon ring as a square. Each point stands for a carbon atom. And then I'm going to write out the group of 2 carbons in a semi-condensed way down there. And I'll draw the chlorine atom up there. I'm drawing in the lone pairs, although it is fairly common to leave out lone pairs when we do skeletal structures. I could make this even simpler by essentially drawing the bottom 2 carbons there as part of the skeletal structure. But again, remember that that's not the preferred method, so I won't use that usually. The condensed structure doesn't work quite as nicely for rings. Incidentally, it doesn't matter at this point whether I draw that chlorine at the top or to the right, and we'll spend some more time talking about that. And that finishes off the condensed structure. Now let's take a look at a skeletal structure which contains a 3-membered carbon ring, a CH3 group, which we will call in a moment a methyl group, and a bromine atom. I'd like you to draw this out in expanded format as well as condensed. Again, please pause the video, attempt the drawings, and then unpause it when you're ready. There is the 3-membered ring of the expanded form. The carbon to the left has 2 hydrogens on it because it had 2 bonds coming out of it, so it needed to have 2 hydrogens. Here I am drawing in the lone pairs on the bromine, even though I left them out on the skeletal structure. And then there needs to be 1 hydrogen and 1 carbon with its 3 hydrogens on it, on the top carbon. The condensed structure doesn't make too much sense for rings, but I'll just write it out anyway. And let's clean that up a bit. There we go, a much straighter looking line. Let's move on to the next structure. Here I'm going to start off again by drawing a skeletal structure. And I would like to have you draw that skeletal structure as a condensed molecule structure, as well as an expanded form. As before, please pause the video, attempt your drawings, and then come back to check your answers. Alright, going from the left, we have a CH3 bonded to a carbon which is bonded to 4 other carbons. Now I've chosen to draw those 2 CH3 groups, one on the top and one on the bottom, because it makes for a cleaner structure. And then I added the next 2 carbons, CH2 and CH3. Alternatively, I could have gotten rid of the 2 bonds in the along the row of carbons there, because this will still mean the same thing to anyone who's looking at it. However, I really need to show those bonds to the carbon above that chain and the carbon below the chain. Otherwise it'll be vague. The expanded structure, as we can see, is going to be a bit of a mess because all those hydrogens would need to be shown. So I need to give myself a lot of space. Let's go on to another molecule. This time I'm going to start out by giving you the condensed form of the molecule. Now I'm showing 2 bonds on that oxygen, but remember there are 2 lone pairs also on that oxygen, even if they're not shown. I'd like you to draw out the skeletal structure as well as the expanded structure. Please pause the video and return when you're done with your drawings to check your work. The skeletal structure's quite easy. So there's 2 carbons, and then those are bonded to the oxygen. And then the carbon on the right side is bonded to 2 more carbons. So you'll notice how I spread them out as far as possible so that they take up the most space. The expanded structure, again, is going to be a bit of a mess with all those hydrogen atoms. I chose to include the lone pairs on the expanded structure. That's usually the case for expanded structures. And here's the last of the hydrogen atoms. And finally, I'm going to add one more molecule that's very important to us. So this is the skeletal structure of a 6-membered ring that contains what we call alternating double bonds. So it's a double bond, then a single, then a double, then a single. Let's clean up that last bond there. And the name of this very special molecule is benzene. It will appear in many structures from here on out. For this molecule, I would just like you to draw it in expanded form. So again, pause the video, please, and come back once you're done to check your answer. So we're going to go ahead and start with our carbons. You'll notice that the double lines stand for double bonds. So I go in a pattern of single, double, single, double, single, double. And every one of those carbons must have 1 hydrogen so that each carbon makes a total of 4 bonds as required. And this ends part 1 of the Chapter 10 videos.